All right, so today I want to talk about a very important article. The title is Attention is All You Need in 2017. And the reason that people write these articles is just because traditional methods like LSTM and GRU, gated recurrent unit, are suffer from very different problems. For example, LSTM, recurrent neural networks suffered from vanishing gradients. That's why LSTM and GRU came. But those technologies like LSTM and GRU, they have some problems. And because they are not scalable, and it is very difficult to scale them. And for long dependencies between, for example, words, you cannot do it very quickly. And so it suffers from bad training. It does not converge easily. So lots of problems in LSTM. That's why the attention is all you need is about a new technology called transformer, and it defines some concepts such as key value and query. So if you understand key value and query, you understand this article. Key value and query. It is analogous to retrieval systems. For example, you want to write something in YouTube. It's a query. You want to search about, for example, computer science or Markov chains. So you want to see the related YouTube videos about, for example, continuous Markov chains, and so it's like a retrieval system, and attention is just a weighted average of values. So C is just the weighted average of some values, and these weights they sum to 1. And so what is interesting is that transformers, they outperforms Google Neural Machine Translation in specific tasks. But the biggest benefit is parallelization. Why? Because there are some new kind of GPUs. They're not GPU. They are designed for just matrix multiplication. For example, a company called GraphCore is designing such CPUs, such systems, that it's a hardware, and it can multiply two matrices much faster than previous technologies. So because in this algorithm, this technology of transformer that I want to explain, everything is just multiplication of these matrices, key value and query, so it can be scalable. And because, for example, it's not sequential. You don't need to wait for the previous steps, and you can do everything in parallel. So let's jump into the idea. And for example, you want to translate this German sentence, Ich bin Farshad. It's a German sentence. So you give it to this transformer, and it gives you I am Farshad. So inside this transformer, there is an encoder and decoder module. So there are a stack, let's say a stack of encoders, encoder. You give Ich bin Farshad here, and the decoder side, in the decoder side, it could be stacked as well. The decoder side gives you the translation, which is I am Farshad. So here you give Ich bin Farshad, which is the German translation of I am Farshad, and the output gives you the English translation. But inside the decoder, you have this architecture. So you have self-attention, and I will explain what is self-attention, and you give it to feed-forward neural networks. So all of these are just the encoder. And in the decoder section, you have the same thing, except that in the middle, you have encoder, decoder, attention. So like encoder, in the decoder section, you have self-attention, first self-attention, and then encoder, decoder attention, and finally the same thing, feed-forward neural networks. So you give the input to the encoder, and then it passes to the decoder, and finally it is now translated. For example, you have done word, you have chosen your favorite word embedding, as I explained, either Glowy or Word2Vec or any word to any word representation. So you have a vector. Your vector so it depends on the size of your vector, but let's fix your embedding to just 512. So you have your input, for example, the first word ish. You have 512 for that, and then bin 512, and Farshad, which is 512. So the size of the vector is 0. And so you give it to the self-attention. And what self-attention gives you is just a vector. So each word, so here is Z1, Z2, and Z3. And finally, as I told you, you pass it to that feed-forward neural networks. And it gives you the result of this encoder. And so this is the first step. But what is self-attention? I want to tell you the details of that. So as the model processes, the word sum itself, attention, allows it to look at other positions in the input sentence for clues that can help lead to a better encoding for this word. So attention is just a map from input to input. For example, I wrote a sentence, most Americans recognize climate, but some are still unsure about its causes. So you write the same sentence here. So most Americans recognize climate, but some are still. So some could be related to unsure. Some could be related to Americans, most Americans, but some of them. So it is related. So some could be related to most of them, 90%, but some of them, for example, 10%. So this is the concept of query that, for example, you want to say this is the query in some keys. And you want to know the relationship between them. So self-attention is the method that the transformer uses to bake understanding of the relevant words in one word, in one word, so that we are currently processing. But the first step is like this. You create 3 vectors, query, key, value, for each encoder's input vector. For example, you have a vector, so each word, for example, most Americans, most. As I said, you do word embeddings, and you now have a vector for the word most. So you multiply this by a unknown query matrix, because your neural networks is not trained yet. After training, you get your W matrix. But this matrix is unknown, but we know the sizes of that. 512 multiplied 20. 20 could be anything, whatever you design. So what you get is the query vector. I'm just doing it for one vector, which is one word, and then you just put it all together, and you notice that it's just multiplication of matrices. Because for a vector, you get a query vector. For 2 vectors, you get 2 query vectors. And then for lots of words, you get lots of vectors, which we call a matrix. And the same thing, you multiply it by the key matrix. The key matrix is 512 multiplied by 20. But these 20 are design parameters. You can choose it as you want. And then you can also multiply it by the value. The value could be 512 multiplied by. So the first one is called query vector. And you know that this dimension 20 is much smaller than embedding dimension. The other one is called key vector. What you get after this multiplication is key vector. The other one after multiplication, you call it value vector. And all of these, we just select one of these. One matrix for value, one matrix for key, one matrix. If you choose just one matrix, we call it single head attention. This is the architecture of single head attention, because sometimes you want to have very different, for example, you want to have 6 different head. So it is, for example, transformer uses 8 attention heads, but your architecture could have, for example, 5 or 20 attention heads. So we end up with 8 sets for each encoder or decoder. Remember. And because finally you just want to put, you have to concatenate it. You have to compress it. So I will explain how to deal with that problem. But what are query, value, and key vectors? So these are abstractions for thinking about attention. So the second step is that you calculate the score. And so the score of each word of input sequence against this word. So score determines how much focus to place on other parts of the input sequence as we encode the word at a certain position. So the first score is Q1 query time dot product with K1 key. So this is a word in position 1. And For example, a second score could be Q1 multiplied by K2. For example, I say French mathematician. So French is in position 1. So it goes here. And same here, is position 1. You want to see what is the relationship between one word and the other words on that sentence. So you got this. And the third step is you divide the scores, divide by square root of your favorite dimension of key vectors, and I chose 20. So 20, we call it dk because this is the dimension of key. And step 4 of our algorithm, you pass the results through softmax. And in step 5, you multiply the result of softmax that you've done in step 4. We multiply it by value, which is v. So the intuition of this step 5 is just, you want to keep intact the values of the words we want to focus on. And finally, in summary, I want to say Z is softmax of K times K transpose divided by square root of the dimension of the key vector, and finally you multiply by value. As I said, in multi-headed attention, for example, in attention head 0, you have Q0 and keys and values, and the corresponding matrices are just Q and W0K, W0V. So it gives you Z0. But Z1 could be the same things, but the attention head is attention head 2, attention head 1, because we started with 0. Attention head 1 is just Q1, K1, V1, and the corresponding matrices, which are W1 query, W1 key, W1 value. So it gives you Z1. But hey, feed-forward layer is not expecting 8 matrices. So we need to condense these 8 down into a single matrix. So we first concatenate all heads, Z1, Z0, Z1, Z2, up to, for example, we have 8 Z7 because we start with 0. So we have 8, so we have concatenated all of the heads. Now it is ready to multiply with a weight matrix, let's say W0. This is the weight matrix that was trained jointly. And finally, the result is Z, and we send it to the feed-forward neural networks. But what we are missing is positional encoding. Positional encoding. Each person can do it differently. For example, you may be interested in sine and cosine. Some other people, some people may need it, may like other functions. So we should also deal with the order of words in input sequence. For example, when I say I am Farshad, I is sooner than a am or my name. So the order matters in a sentence because, for example, when I say I go there, it's different from go and then something, because when the verb is at the first position, then it becomes some imperative meaning. And so transformers add a vector to each input. For example, when I say Ich bin Farshad, you put it before you put it to the encoder. It has an embedding. This is the embedding, word to vec. This is embedding of that, and then you add the positional encoding. So you add this vector to that, add this vector to that,